Ladies and gentlemen, my name is Richard Rutkowski, and I will be your host during Additive Manufacturing Panel. 3D printing is a hot topic since many, many years. Some of the companies already introduced that into their shop floors, while others are still considering that. Is it worth it? What will be the future of additive manufacturing? And what role plays heat treatment in the entire process? We will try to find answer on those questions with our today's specialist. So please let me welcome Mr. Mark Barfoot, EWI, United States. Hello, Mark.
Hello, how are you?
Yeah, quite well, quite well. Hope you are doing the same way. And Mr. Oliver Hanitzsch, ExOne Germany. Hello, Oliver. Good to see you.
Hello, Richard. Pleasure to be here.
Same, likewise, Oliver. 3D printing is not only a hot topic, but is also extremely wide area of activity. This is the reason why we will try to put everything in the right order with Mark's presentation. So, Mark, whenever you're ready.
Okay, well, thank you very much. Well, today's presentation, I'm going to walk through the state of metal AM, an idea of where metal AM is and what challenges and trends are in metal AM. Just a little bit about EWI. We're a not-for-profit organization here in the US. We help companies de-risk and adopt new technologies. We started as a welding institute. We do a lot of forming. We do a lot of metallurgical heat treat studies and other studies like that, as well as additive manufacturing, which really is welding over and over and over again. Kind of where we come in is, people come to us with their product requirements, and then we help them select the process, select the material, all the post-processing, including the heat treating, secondary machining, finishing, as well as the NDE techniques on, how are you going to inspect these parts afterwards. And really, with additive manufacturing, you need to think about all these things to get that to work well. We also have an additive manufacturing consortium. This is a group that I run, so this is a group of member companies. We've been going for over 10 years now. Started with aerospace, had a lot of other industries involved as well. This is just a group together. We network and we do research projects together, and so it helps de-risk some of that early stage challenges especially around metal AM, and so that's another area that we get involved in. So talking about metal AM, one of the big misnomers with metal AM is it started yesterday, right? If you listen to the media, they're all about, hey, it's early, it's only been around for a few years. Well, no, it really started back in 95 was when metal AM started. Plastic AM was even earlier than that, back I think 87 or something like that. So huge changes over the years, and I would say metal AM has really started picking up speed over the last 5 to 7 years or so. That's when companies started to look at using it, and it's still early stage, and we're going to talk a little bit about that throughout the talk today. AM technologies. Anybody looking to get into metal AM, it is a myriad of different technologies, and this chart is one Digital Alloys supplied to me, and as you can see, it's all these different technologies, all these different companies. Each one has a different type of method they use for metal AM, and it can be overwhelming for people that just get into it. Which one do I need? What do I use? And each one, they're kind of different tools in the toolbox. So it depends what you're trying to do and where you need to do. And this is what we get involved in a lot, is helping companies figure out what technology makes the most sense. We'll start off with one that's the most common. You've probably heard of DMLS, laser sintering, metal laser sintering. This is one of the ones that gets the most media press. It really is being utilized the most at this point. Basically, you're a layer of powder, a laser, solidifying that layer, lower the tray, spread another layer of powder, and build it up again and again. So you're really just welding those layers of powder on top of each other. It creates really strong parts. You get really good resolution. You can build a ton of different materials with it. As with any metal AM, one of the biggest challenges people don't realize is the powders can be explosive, especially as you get to aluminum and titanium materials. So you do need to be careful as you think about setting it up. And other challenge with metal AM, everybody comes to me and says, hey, I need to make this massive part. Most metal AM technologies is not there yet. Most machines are around a 10-inch cubed volume. There is some a bit bigger, but again, the larger the volume, especially in this technology, the slower the build. And so it's going to take a while to get those parts built. And what kind of parts can you build? With metal AM, it's a wide range, everywhere from aircraft brackets. The part up in this top right corner is from GE. It's the GE fuel nozzle. I'm sure everybody's heard and seen about that. That's the one where most people are about production for metal AM. That's one that's really into it. Things like dental implants, though, many of those have been printed for the last several years, and that's the way they're producing them now. It's just more cost effective, a better way to do it. So powder bed fusion is definitely an interest to a lot of people. The other one is extrusion-based material, or binder jetting. And Oliver's going to talk a little bit more about binder jetting, so I'm not going to go into the true binder jetting, but one of the new realms that has come out is this extrusion-based metal. So it's using similar principles to Oliver's ExOne technology, but this is extruding out a ribbon of material. So you're using, imagine like a weed eater cord, but in this case, you've got metal particulates spread inside that plastic binder. And basically, you're just laying that part up layer by layer, and then you go through all the sintering, heat treating processes, just like you would have to do in a regular binder jet process. It's had a lot of media press in the recent while because it's not got hazardous powder, but it's not going to be as strong a part. You're going to have more potential to break between the layers. The other challenge with this technology is it also builds with a lattice structure inside it. Many people don't realize that. So it's not building a solid part, especially if you have a very beefy part. It's just building a lattice. And so, how strong that is it going to be representative of your final part? May not be. So you need to think through those things. Just a couple examples of some of those extrusion or binder jet processes. You can get parts also do shrink. So, and Oliver, I'm sure we'll talk about that as well. They do shrink during the, so you need to account for that, about a 20% shrink. But it's very similar to regular powder metallurgy that we're somewhat familiar with. This is another technology that's new. This is one that actually EWI developed, and we spun off a company called Fabrasonic. This is where we're laying up thin sheets of a film. So basically, imagine just a little wee thin strip, and then we're ultrasonically welding it onto to the layer below. And then you build up another layer, do the same. In between those layers, you have the option of CNC cutting to cut out your shape or your geometry. Big advantage is there's no heating involved here, so you can easily embed electronics into it. You can mill in slots and embed sensors or other items. You can also bond a lot of different dissimilar metals, which really does help and is unique. A lot of the other technologies can't let you do that. Material jetting. This is a new technology. It was launched back in May of 2016. They were at Formnext last year. They're starting, but it's still relatively new. It's called Nanoparticle Jetting. So basically, it's based off somewhat the polyjet technology that was with plastics for years. We're now, instead of using, so they're using like a inkjet print head that's basically spraying these nanoparticles down, and then you're sintering the parts afterwards. It gets you really, really fine resolution parts, but they're really relatively small. So depending on the geometry, it could be a fit for what you're trying to do. Material jetting, this is another one. It's slight variation of material jetting. This was originally announced by a company called Vader, which was bought by Xerox. And Xerox has just now re-released that product at Formnext last year. And it's called using a magnojet. So basically what you're doing is you're depositing an aluminum wire into a 1200 degrees Celsius ceramics chamber, and then it's changed into molten state. And then you magnetically pulse it, and then you get that droplet coming out in a very precise manner. Has potential to build at a much faster rate than some of the other technologies, uses that low commodity wire, so it has a lot of potentials. How does it work? We don't really know yet, because it's still, I don't know of anybody that has a machine yet. It's still in that early development stage. And now that Xerox has it, I'm sure it'll come to fruition. It's just a matter of seeing how that technology comes around. This is another one, jewel printing. So I'd mentioned digital alloys that supplied that initial chart. This is one where they're using essentially resistance heating. So you're basically feeding a wire, and then you're basically, through resistance heating or resistance welding, building up that layer. And it allows you to move continuously and fairly fast. So you get very fast build-up. They also have a camera system that lets them do some closed-loop control to optimize their build parameters. And so, again, fairly early stage. They're not planning on launching till late this year, early next. May have changed a little bit with COVID. But again, high build rates, up to 10 kilograms per hour. And I'll talk a little bit about the trends, and that's definitely one of the trends, trying to get faster build rates for these technologies. Layered powder metallurgy. This is one that Stratasys announced at Rapid 2018. They've been somewhat quiet about it over the last few years. I think it has a lot of potential. They're just now, they launched it, but now they're really trying to get this technology to work. And we don't know a ton about it. We know that there's a printing stage, there's a compression, compacting stage, but it's meant for aluminum components. And it's supposed to be very fast, 9 times faster than laser powder bed presses, and relatively easy support removal. The support just kind of falls off the parts. We don't know a whole lot more about it. We think it probably has to go through some sort of a sintering stage. So it's sort of like a binder jet process. But again, there hasn't been a lot of information, a little bit. If you Google it, you can probably find a video that kind of explains it a little bit. But again, it's very early stage, but has that potential. And there could be potential for production type volume. And that's really where we're seeing a lot of these metal technologies moving towards. Cold spray additive. This is another new technology. So SPE3D out of Australia, they're one of the ones that have been most focused with it. And they provide very fast deposition rates. When they're talking build times, they're often talking, in minutes, not in hours or days like we often do in laser powder bed. And so it gets you a near net shape, but does typically require post-machining. So it's very similar to a lot of the DED processes or direct energy deposition processes, where you're feeding a wire, you're feeding powder, but you're not actually, you're getting more. But you can build very, very rapidly. The other is this technology allows us to build with things like copper. So copper in a lot of technologies is very hard to build with. The SPE3D system works great. And so you can see a couple examples here. That part up on the top is a copper base with aluminum fins. So imagine a heat sink. So you can take like a standardized heat sink and then lay up the copper underneath so you get better thermal conductivity. The part on the bottom is like an electrical conductor. 25 minutes to print it, $38 cost, relatively low cost, and now you've got a high voltage terminal. The other thing that SPE3D has been great with this environment we're in with COVID is they've determined that one of their coppers they were able to tweak a little bit, and it is supposed to provide an antimicrobial coating so that you could put it on a door handle or a touch surface, and it'll help reduce the spread of COVID. So that's kind of unique about that technology, where AM is actually trying to help against the fight against COVID. So for the last part of my presentation, I really wanted about the challenges and trends in metal AM. This is where most people get involved, get excited about. There's a lot of media buzz out there about what the trends are, but so many people get confused to, is this something that's viable? Can I do it? And, I just went through really quickly there 3 or 4 technologies. Those are kind of some of the new up and coming technologies. Like I said, there's a whole range of technologies, and it's really hard to know, which one makes the most fit. But there's also, within all those technologies, there's several trends that they're all kind of leaning towards, and that's what we're going to kind of walk through now. The first is standards. This is what's holding AM back in a lot of cases, is that we are lacking those standards. So how do we qualify it? We have our injection molding standards. We have our casting standards. We don't necessarily have all the standards for AM. So ASTM is one of the ones that's leading that forefront. They have an F42 committee around standards. And EWI is actually part of that group. We have a center of excellence that we're joined with ASTM. You'll see the links there with EWI, NASA, NIAR, NAMIC, MTC, University of Auburn, and a few other partners that basically are trying to short up this. So we're basically working together using consortium, using direct research projects, going after government funding together to basically develop these standards. And that's really what's one of the gaps, right? A lot of people are, if they qualify an AM part, have to do it all manually with their own process. If we can get away from that, that's going to speed up the adoption. The second part is powders and parameters. People get confused. They buy powders and then they are like, well, that powder didn't work. There is such a wide range of powders out there, and more companies are like, I want to get onto the AM bandwagon, I'm going to start selling powder. Well, I have to say, not all powders are created equal. If you look at the three pictures here, that top part, that's a very spongy-like powder. That is not going to build as well in an additive machine as something nice and spherical like the bottom right. Or you look on the other bottom picture here to the left, you can see those big circles. Those are porosity in the powder. So if you get that porosity in the powder, that's going to naturally reflect into your actual part. So it is important, if you're looking into getting into AM, think about your supply chain, think about your powders, and how do you qualify those powders? How do you inspect them, making sure that they are? The second part around powders is the parameters, and this is where we get involved in a lot. Companies, when you buy an additive machine, you get a parameter, and it's kind of a jack of all trades type parameter, something that'll work to build large parts, something that'll work to build small parts, but it builds neither of them perfectly. It'll build them, but they're not necessarily the best way for your application. So what you really want to do is you want to dial in those parameters for your specific application, and that's what we get involved in a lot. We've also seen a trend around new alloys. That's the advantage of metal additive. You can mix different alloys, mix different additives in, and now you can come up with something new in a powder form that we can probably print with AM. So that could be a strong potential for us. Heat treating. This conference is all about heat treating, and I have to mention something. I am not a metallurgist, so I'm not going to go into full detail on it, but this is another area we get involved in a lot. Not me personally, it's our metallurgical team. This is just identifying a study we did a while ago where we did a whole chemical analysis of parts, and then we did a whole range of different heat treating methods. And so you can see different temperatures, different times, whether it was argon cooled, and then whether it went through a HIP process as well. And so we try to see where those fit. And just a couple quick snapshots. There's a whole paper around this that I'm happy to send to you if anybody's interested. But you can see, this is just three different of those heat treat cycles. A 15-minute cycle, you get these intergranular precipitates observed in the microstructure. After an hour, the finer grain interiors are almost completely depleted, and then you're getting more of that grain boundary precipitates, and they start to get larger and larger. And then after the 8 hours, you got significant grain growth. And as you can imagine, each of these are going to give you different mechanical properties. And so it's very important to look at your build, look at the parameters, and it does vary a little bit between the technologies. So it's not just you can take a powder and know that you have the right heat treat. You need to take as-built parts and heat treat those and determine what's the optimum one for your process, your material. The next point is speed. I already mentioned that. 3 or 4 of those new technologies I talked about are all about speed, right? Getting to the build faster. I mentioned SPE 3D in the bottom left there. That's all about speed. You get the fast build, but then you got to post-process it. The bottom right, ExOne, Oliver's going to talk shortly. Binder jetting is a great process. It's able to build very fast. You get some shrinking. There's different and challenge maybe around it, but that's where a lot of people are looking at binder jetting as a solution to get to that faster speed. And then on the top right, this is the other trend is using multi-lasers. So this is a regular laser powder bed, and this is an example from Renishaw. So in that picture, on the far left, the small build, that's with a single laser in the same build time. So you can see how high it built. It only built inch and a half up. The one in the middle is built with 2 lasers. Now it was able to build a 3-inch type part. The one on the right is built with all 4 of their lasers, and it built it, in the same time frame, you're able to build your entire part. So it's a way of allowing faster builds. Often too, the multi-lasers allows larger builds as well because you can spread them out over the build tray. In-process monitoring. This is another area of a lot of research. This is an area we've spent a lot of research on. If you can sense and monitor your laser powder bed, some of these laser powder bed builds are, hours long, if not days long. I know NASA sometimes builds months long. Well, you want to know that something went wrong halfway through, quarter of the way through the build. You don't want to know at the end of the build after you evaluate it and find, hey, that failed. I'd rather stop the build now and read it than to wait a month or wait 3 weeks or 2 days and then have it fail when I did the post-evaluation. So looking at those sensors, how can we detect what went wrong? The other avenue of that is how can you detect it and then correct it moving forward? That's an option as well. And we've done a lot of work in some of that as well, whether it be for a laser powder bed or for the DED processes. Machine certification. This is another avenue. We talked a bit about standards, etc. CNCs, we have a standard process to qualify a machine, make sure it's everything's true, everything's running correctly. We need to get more on that. So it's not just, how's the airflow, how's your movement of your elevator, or the picture on the left here is talking about a new spot size calibration system that we have where you're actually optimizing the laser itself. And so it's a great option. And there's a lot of research around that. How do you know your machine's right? Or how do you know this machine compares to another same machine of the same manufacturer? Or how do you compare that machine to a different manufacturer's machine? And that's the challenge that we're getting around the standard side. And then, on the right there is other ways of monitoring. Is there other things we can look at for using monitoring systems? Eddy currents, melt pool size, light intensity, powder temperatures. Can we put temperature sensors throughout the build to know where we are? Can we sense the build plate that it's warping or twisting during the build? So all those kind of evaluations will help us know and confirm that we're getting good parts out at the end. Automation. This is another, manufacturing takes a long time to build, but it also can end at hours. If you got a build running at till 2 a.m., it would be nice to be able to have that machine automatically shuttle it out of the build and restart the other build without having to have an operator there. And that's one of the trends. Additive manufacturing or Additive Industries is one of those companies. This is their large machine where basically it'll shuttle it through 3 or 4 different stages and completely allows lights out involvement. And then when you come back in the morning, you clean up whatever stage it's at, and it keeps running. There's other companies that are starting to come out with similar automation, whether it be standalone automation on the side or integrated more like this system. Cost. This is the other area. When people started, and part of the reason Metal AM took a long time to start taking off, you were talking at least $1 million, $2 million machine. Those prices are coming down. You can get, $500,000 machines, $600,000 machines. But now we're seeing a new class of machines. The exact metal system up on the top right, that's now somewhere in the $90,000 to $150,000 machine. Well, now you've got laser powder bed capability at a much lower price point. Smaller build size, 5-inch by 5-inch by 5-inch, but a lot of the time that's the size parts we're building anyway, so this type of technology can make sense. Desktop metal on the bottom left, this extrusion-based process, it's also claimed to be a lower cost. Now, the machine itself is relatively lower cost, but then by the time you buy all the sintering oven debinding, it can add up. It's probably a little more than, around a $250,000 investment. Still a long ways away from $1 million investment, but it has that potential to get into it. We're also seeing more and more vendors come in. We've seen some Chinese vendors, we've seen, European vendors as well, many that are getting into this market. And so as we get more competition, more vendors, I think we're going to see more and more companies come to fruition. Software tools. Simulation, you're going to see part deformation, you're going to get there's lots of different simulations you can do. You can determine the residual stresses. You can imagine you're building a big solid block up. It's going to warp. It's going to twist. And how do you qualify that? How do you know what's going on? Again, you'd rather do that simulation up front and know that it's going to build instead of starting that build and hoping that the 48-hour build is going to work. There's a lot of different tools out there. Are they perfect? No. Are they getting better? Yes. And so hopefully we can see those tools work out in the future. The other avenue around software is just programming the systems. So robotic DAD systems, they've been around for a while, but they've been very limited use because of the software is not there. Many of these systems for years, my whole first time with Additive, it was all involved with, manual G-code programming, very complex programming to be able to do this type of geometry. Now, as you can see, any marks, ones that are already built into things like, Power Mill from Autodesk. So you're able to do a lot of this type of geometry now using their tools. It was developed from a 5-axis CNC machining capability. Now we need to port that same capability over to 5-axis additive manufacturing or 6-axis additive manufacturing. And so, there's getting more and more traction, more and more software packages that allow us to do it, which helps you do those more complicated parts that you want to be able to do. Large scale. As I said, many people are trying to get larger build sizes. The DED process in general is one of the processes that does allow you to get a much larger build size. You're talking, feet size builds versus, a 10-inch type build. And so, this has a huge benefit. So this is an NSRP project that we've been working on where we're able to build, large structures, add features to structures. That's the advantage of DED. You don't necessarily need to build the full structure. So for example, this, turbine blade, you can start with a solid round core and then add the turbine blades onto it and then post-machine them afterwards to get that smooth surface finish. So this is one of the projects we're working on. And we're in the middle of we have a large gantry-based system at our facility. This is basically looking at doing a research to make even a larger scaled system. And, to put it in perspective, I think this turbine blade is around almost a 2-foot diameter blade. This is 25 feet by 15 foot by, I think it's 9 foot high type build size. So much larger size parts, but again, more near net shape, not necessarily final build size. One of the last struggles we have is training. How do you train your employees? Most of the universities, most of the colleges just don't have good training materials available. Most times, if you're at a college, it's a course or it's a series of courses. We're starting to see some colleges that have a manufacturing minor that you can kind of get into. A few colleges are looking at additive manufacturing programs, but they're still very early. So, how do you get those people that you can do? Most people are having to train those internally. The other thing with training is how on earth do you as a company come up to speed? How do you weed through all these technologies, right? There's a lot of different technologies out there, and it's a challenge. I've been in the industry for almost 20 years, and every time I turn around, there's another new technology, another new company that's doing something slightly different. And the challenge is they all call their technologies almost the same name, slightly different, but a little bit different name. And so it's hard to know, is that just the same type of technology, just with a different name, or is it truly something revolutionary, truly something new? And that's where we get involved, our Additive Manufacturing Consortium. This is actually an image from it, where our members get together. We're sharing some of those technologies. We're trying to work through it together. And that's what I try to get involved, try to form. Show AMUG or Rapid or FormNext. That's where you can see all those technologies and start to understand, talk to people, learn what it is. The other avenue of training is getting people into the additive manufacturing mindset. Contrary to what people would think, sometimes your seasoned operator is the harder one to actually get adopting it. The young kids out of school seem to get it faster because they don't have those preconceived notions, right? Those of us that have been designing for a few years know there's, you don't violate the casting rules or the injection molding rules or all those processes that we've been taught as we've grown up. Now with additive, some of those can be thrown out, but there's new rules that you have to abide by. So you do need to be able to think outside the box. You don't want to just take your exact additive part and change it to be built with additive. If you can CNC machine it, it's probably the best thing to CNC machine it. What you want to be able to do is pick a part that then you can't make any other way. In summary, there's a lot I've went through here. There's a lot of trends. Things are changing very rapidly in the industry. The first thing I can say, don't be afraid to try it. Try and get involved. Can't machine, get out, find a bureau. Lots of bureaus, and as well as around the world that will print parts for you. It's a great way. That's what I started with, right? When I started with Christie 20 years ago, we started bringing in parts. Then we realized, hey, we're outsourcing enough parts that it's better for us to bring the technology in-house. And then once we brought one technology in-house, we started expanding and bringing all the different technologies in-house. And that's the one other challenge people have is they're like, well, I bought this one technology, I expect it to do everything. Not every technology is going to be a fit. Little benefit of what makes the most sense. So you're best to fit the technology to your industry. Seek out those knowledgeable experts. Companies like ours, and there's others out there that can help you determine what's the right fit, what's the right process. Build out those early prototypes. The other point is get a champion. The companies that I've worked with that have had the most effect are the ones where they have that senior person within their company that's just phenomenal and has really grasped what additive can do and is then able to sell it through the company. That's really going to help get it adopted through the company. Break down those barriers in your company to allow AM adoption, whether it be cost, whether it be structure. Because, for example, in additive, it's probably going to be a little bit more cost to produce with additive, but the long run gain is there. Metal additive especially, it's not just about building this part, it's about the whole value chain. The part itself may be more expensive, but as you process that through your whole process, an aerospace part is more expensive, but it saves thousands, tens of thousands in fuel over the life of the part. Or maybe you don't have to have an inventory control. Or you're getting the part in 3 days a week instead of 16 weeks, 18-week lead time. So factor in all those kind of things. And that's where you need that champion that can see beyond just that individual part. I'm excited. I think we're going to see a wider range of adoption beyond aerospace and medical as we move forward. That's the two industries that have kicked it in, but we're seeing more and more people start adopting additive. And I'm excited to see where it's going to go. It's changed so much in the 20 years that I've been doing it, from early prototypes, and that's all we could do, and the parts were very weak, to now fully functional parts that we're integrating into production, fixtures, metal, being able to actually produce metal parts that are fully functional, meet aerospace, meet medical grades. As that gets more and more evolved, as the standards get developed, we're seeing more and more companies get involved. And I think it's something to look at. If you haven't looked at it, feel free to reach out to me or to others. We'd be happy to help you with that. So thank you.
Well, Mark, thank you very much for your knowledgeable presentation. There was an astonishing overview of entire, I believe, technology available on the world. So thank you very much for it. Actually, I've got a few questions to the presentation. The first refers to the future of the additive manufacturing. We were saying a lot about the past, about the present, and I believe the future is quite bright. But in the long run, what do you think? In which direction it will go? Shall it be more a kind of niche technology for niche production, or maybe it will totally dominate traditional way of production that we know today? Or maybe somehow it will coexist with current production standards that we know. What's your guess about that?
So I don't really see AM completely eliminating, our traditional manufacturing, right? It's hard to have AM compete with traditional casting, traditional machining. Again, if it can be produced traditionally, it's probably a better fit to produce that part traditionally. Where AM fits in is where you can combine parts together. You can make geometries that we can't cast or we can't CNC machine. That's really where the fit is. And so that's where I see it being more adopted as more and more people get into it. Customization is another area we can see in the future, right? Why do we have to always have the exact same part? Why don't we customize it for that individual, that person? And so, that's really where we see the future of AM going. I don't see it replacing our technologies. It's just another tool in the toolbox, right? It's, you don't use a hammer for everything. You shouldn't use AM for everything either.
Fully understood that, fully understood. You also mentioned it in your presentation that there is certain area where the knowledge can be boosted. In case someone would like to implement additive manufacturing to their shop floor and there is not much knowledge in-house of the company, what is the best way to do that in the right way?
Yeah, that's a good question. I kind of alluded to it a little bit. Best is, there is a bunch of different consulting companies out there that can help you get through that knowledge. The other avenue is go to trade shows. Here in the North America, Rapid is a great trade show when you're just getting going, trying to understand the technologies. That's where a lot of the companies come. Formnext in Europe, that's a similar, much larger show. Everybody's there. It can be overwhelming, but it's a great opportunity to get to see people, and that's over in Germany. Once you've got your machine and you're really getting to know how to use it, AMUG is a great event that you can go to. It's an additive manufacturing user group, been apart for a lot of years, was a few years ago. It's more that networking and sharing. So you've got this piece of equipment sitting on your floor. How do I use it better? Talking to like-minded people. This technology is still relatively new. So many times, user to user learns more about how to use the machine than even the manufacturer, because we're the ones pushing it to the limit. Manufacturers sell machines. They don't necessarily use the machine on a day in and day out basis. So, seek out those people. Don't just try to do it on your own. That's where I've seen the biggest challenge. People get confused or not able to do that.
Yeah, especially that we have seen that there is so many options available on the market. So probably it is not easy to choose the right one that will fit us perfectly. That's nice. That's nice. One of the last questions will concern ecology. There is a lot of going on these days with eco-friendly solution. And in general, do you think that additive manufacturing as the concept, is it an eco-friendly solution for the companies and for our world?
Yeah, so, I get asked that question a lot based on each technology. So if you're looking at the plastic side, many of the plastic systems they're building with, ABS, polycarbonate, et cetera. Those are all recyclable plastics, but you need to be able to set up your supply chain to be able to recycle them properly. And so that's where you can, make sure you've got those plastics identified so that and that's the biggest challenge. They need to know which plastic they are. If they don't have the identifier on it, it's harder for them to identify. On the metal side, all of our waste is recyclable, right? It's powder. So you can reuse it, you can remix it. The big advantage of AM is, though, you're only using the powder you absolutely need. So instead of taking a 100-pound block and machining it down to a 5-pound part, you're using maybe a little more than 5 pounds, but you're using 6 or 7 pounds of material. And so naturally, you're not using as much material. Now, right now, many cases we're using virgin material to try to get better material properties. There's lots of studies out there on recyclability. How many times can you reuse the powder before it starts going bad? And then once it is bad, can we just run this powder back through a plasma atomizer, for example, to reclaim it and get it usable? And so there's been a lot of studies, a lot of work on that. We have a plasma atomizer in our facility. Showing that is potential. And so there's a lot of eco ways to do it. Certain technologies, no, you got to scrap that part, especially on the plastic side, the stereolithographies, the polyjet type parts. They're just waste stream. But a lot of most of the metals you can recycle in some manner, and many of the plastics. So, inherently, I think AM is a more eco-friendly. Also, the other avenue of eco-friendly is you're reducing your supply chain basis. So you don't have to have all these parts sitting in warehouses that you don't need. Now, all of a sudden, 10 years later, when your product's obsolete, you're scrapping all those parts. Instead, just build the parts as you need them for a repair, standpoint. So, there's that avenue of eco-friendly as well.
So I believe that's another good point for additive manufacturing once again. My last questions in this part of our panel, I would like to dedicate to you both gentlemen, so Oliver and Mark. Lately I have seen some trials, the guys were trying print food, particularly speaking steak. And the question is, would you like to have that kind of steak on your dinner? Oliver, Mark, I know that you are an enthusiastic in terms of additive manufacturing, but how about food? Are you open for that?
For sure.
You go first.
Sure. So, I've traveled around the world. I've tried a lot of different foods. So why not an additive manufacturing steak? I've seen a lot of interest in printing in foods with additive. I'm up for it. If somebody's got it available to try, why not?
Exactly, exactly. For me, it sounds a little bit hardcore as well, but I will give it a try as well. How about you, Oliver?
Actually, I think as we are in additive, we have to try it. That's for sure. And as long as it is medium rare, I would love it. And I think I've tested chocolate already being printed. There's a lot of things. And let's be open-minded. So give it a try. I think that's the way we should go forward. And probably it's not as bad as we think, maybe.
Probably so, probably so. I didn't have a chance to taste it, but if I will have, I will definitely go ahead. So thank you very much, gentlemen. Mark, once again, thank you very much for your presentation. It was really extremely knowledgeable, and I believe right now it's about time for one of the most promising technology in terms of metal 3D printing, which is a binder jetting and ExOne. Oliver, it's in your hand right now.
Thank you, Richard. Thank you, and pleasure to be here. Pleasure to present binder jetting and ExOne. I will walk you through the presentation as it comes, and it's about the company. It's about let's say the history of the company and a bit of the history of binder jetting, as well as the technology as such. So the first slide is that's me. You can find me in LinkedIn. If you have further questions, don't hesitate and send me a message. A news to me, company, that's more important than me in that case. So basically what is important to me to tell is that binder jet, and this has been shown by Mark as well, additive is around quite longer than people expect, and especially in that case, binder jetting and ExOne. So we are in that business in 3D printing over 20 years now. We started in '95, and over that time, it took quite a while to optimize the process, to fine-tune the process, to not reinvent the wheel. But the unfortunate thing is that such kind of technology, it does not start with generation 6 or 10. You need to go through generation 1 and generation 2, which is, of course, not as advanced as it is today, but you have to start at a certain point. And that's what we did as ExOne. We started with binder jetting more than 20 years ago. And this gives us kind of a head start talking about binder jetting as well. We do that not just for metal, we do that for sand printing. On the right-hand side, you see a sand printer, and on the left-hand side, you see a metal printer. And I will talk about that a little more. So these are the markets where ExOne is basically focused on. On the left side, you see 3D sand molds and cores for metal casting. So the printers printing sand and big cores and molds. And then in the middle, we do have we call that direct metal 3D printing. That means really binder jetting into a powder bed of metal. And then the next step is curing, depowdering, and sintering. Then as well as it is as well available in powder form is ceramics. And as ceramics can be sintered as well, we can print green bodies, green parts with our technology and our machines as well. So these are the three markets ExOne is covering. Where are we? We are almost the most important areas in the world. That is Asia, of course. It is in the middle of Europe. That's Germany in that case. And we are present with our headquarters in North Huntington. So this is where we have our our bases, and the area which we can cover, you can see it's quite all over the world. As somebody is interested, we can cover his needs. As a decent company, of course, we do have collaborations in place with other universities, with other companies, because in additive, I think that is what Mark has shown as well, and it's important to understand it's about doing that together. The market is not mature, it's really new, it's a young market. We need to do networking, we need to push, we need to train people and to educate people, and therefore you need a network as it comes. You need universities, you need other companies collaborating to make the push, because nobody can do it on his own. That's not possible in that area of applications of technology. You need a cooperation, you need partners, you need to push, because it's so new. It's not around. Yes, it is around since ages, but as it gets more traction, you need to make that more visible into the common markets. And where it does fit into, it's a nice fit, but sometimes it just doesn't. And we need to talk about that. So the company history, just to give you a flavor, we started in the 95, quite some years ago. And what I want to point it out is that, for instance, in 2003, we brought to the market the first metal printer. 2003, which means this machine is running still today in one or the other facility. And then the next milestone, which is important to me, is the 2018 and 2019, we launched a new generation of machines, considering a little different technology of recoating, which enables us to print MIM-like powders, so very fine powders, with our technology in the binder jetting area, which is quite unique. Well, the history of metal 3D printing, everybody knows that kind of graph, where it started and where it hopefully will go. And we are not as advanced as we are in the sand business. Sand printing, it's a little longer around the corner here. You see that we have already reached that kind of status in maturity. There's machines placed in companies. They run almost 24/7 operations. So this is what the ExOne company, we build machines for sand printing, we build the machines for metal printing. And how does that binder jet work? A little overview, and a little overview where it hopefully goes to. So basically, we start with, we have a powder, we have a binder, and we print layer by layer. So this is the core technology. And of course, it's not as easy as it looks like, as always, if it comes to AM. But the nice picture here on the right-hand side is same as Mark has predicted, that as we have higher build rates, we have low operating costs with that kind of technology. There's a big opportunity to grow into the market with that kind of technology. The binder jetting technology, there's a lot of space, and there's a lot of education, a lot of training necessary to tell the people what is behind that technology. And no, it is not replacing milling, drilling. It is a niche in a niche, but if you find the right place, it is a nice technology. Well, of course, most of the people have talked and have seen some of these predictions where the metal 3D printing will go, and where is it already ready for mass production? Kind of still learning phase. Some technologies are more than others. Probably binder jetting is a little closer to the mass production compared to the powder bed fusion, laser-based, or maybe E-beam based. But at the end, there's room for improvement for all of us. There's a big industry out there which hopefully will understand what is the advantage and the capabilities of that kind of technology. Let's go through. Mark has started to tell you already about the additive manufacturing or 3D printing. that's a little different. If you ask Google, hey, Google, tell me what is 3D printing, then you get that kind of pictures. That means it's more plastic related, not that much of metal. So interesting thing is that if you go for, hey, Mr. Internet, what is additive manufacturing meaning? And then all of a sudden, you get more pictures and results, hits metal related. And there, just by giving you that two little simple examples shows, I think, that the landscape of 3D printing, of additive manufacturing is so diverse. There's so many technologies. I'm really impressed by how EWI is doing it, because there are so many new technologies coming around the corner each day, and you need to scope with that in terms of what is, as Mark said, is there a difference? Is there the same name almost, same description almost, but a little difference? So it's a big landscape. At the end, what we are going to concentrate today on powder bed combined with the binder jetting technology. And as we speak about this kind of, there's so many abbreviations, acronyms flying around for binder jetting, the powder bed fusion, and I personally sometimes I don't know each and every of them. So we are going to concentrate on the binder jetting, the technology, and there is much more out there, which is good. On the other hand, it's sometimes hard to explain where are the differences, where is the advantage or the disadvantage. Let's go for the binder jetting technology, most simple. There's a powder bed and there's a print head, which is printing into the binder, into the powder, the binder, which is kind of a glue, gluing together the particles. And as this is kind of too simple, I will show a little video based on the sand printer, but it gives you a flavor how the process is going to work. And which is important is to understand the recoating system, the recoating, how that is going to be done, and to jet specifically, precisely a droplet of binder where you want to put it into the powder bed. So first step of the process is the recoating process. We need to put layer on layer on layer, layer by layer, and that, of course, that video is a kind of artificial because the particle sizes are looking all the same, but it shows how it works, that we put a layer of powder on top of the other layer of powder of particles. And here, the next step is then to firing the right amount of droplets, the binder into that, on top of that layer, at the right place as we want to be put it, and this liquid binder is then jetted by the printhead into the powder bed, and it just kind of glues together the single particles to a green part, which gives us the ability to cure that green part, and then we go into the sinter process to sinter that green part. Product overview, just to give you a rough idea. We do have the sand printers in our portfolio, 3 different models of it, and we do have 4 models, 4 machines for the metal printer, which we supply to the market. And the nice thing is that we have as well machines for the R&D purpose, being able to be run by one person only. It does fit into a normal laboratory door. And then we have, of course, more the production system, production machines, which have a bigger build room and a higher throughput. Basically, all of them have this, we call the triple ACT. That's a technology I will explain some slides later, which is enabling us to spread out, to recoat the powder in a way we wanted, and to have the same technology in the R&D machine, which we called Innovent Plus. And then we have the same technology of recoating in our production machines, enables this kind of scale up into production from R&D pretty smoothly and pretty linear, which is our target to give the customers a possibility to translate their R&D results into production. The ACT technology enables us to handle a powder, and we have learned by Mark's presentation there is a lot of difference in powders, and I can tell you he's so right. The powder the people are more familiar with, that's the most optimal powder, is very spheric. There is no satellites, it's flowable, and all these things. But at the end, if you want to go into a more productive way of producing binder jetting, you try to go for MIM powders, metal injection molding powders, which are typically having a D10 of 22 microns. So that means it's quite a very fine powder. And as it comes, physically, fine powders, they tend to stick together. The particles are sticking together. They are no longer that flowable. And therefore, we have invented this kind of technology, which enables us to recoat even very fine powders. So we do have an ultrasonic hopper and a spreading roller and a compacting roller. And this combination of ultrasonic hopper and the two rollers gives us the possibility to recoat even a very fine powder. And this is of importance if you want to decrease the cost of the powder in the future, because MIM powders are available as the MIM companies, metal injection molding companies, use that very often, and tons of that material, so we can use the same powders with our technology. Here you see that a little more in detail, how this that ACT does work. The advanced compaction technology, we have this ultrasonic hopper, and by being dispersed through the hopper, we have two rollers which are leveling out and compacting the bed we put on top of the layer we put on top of the other layer by powder, layer by layer. And it's a very constant and very homogeneous way to spreading out to recoat the powder, which is important if you consider that at the end we will build a part which has to go through a different process at the end, which is the sintering process. And as better, as more stable and more homogeneous the green part is going to be, as better the result is going to be after the sintering process. Let's have a quick look to the machines as such. R&D machine, we call that Innovent Plus. It has a small build room, but most of the time enough build room to make a small part, to do the first tests, to do the development work with one or the other machine material. And the nice thing here is that you can change over the materials quite easy. If you go for an iron-based alloy, or you want to change for a nickel-based, you can change by having a clean time of less than 2 hours. The big machine, which we call 25 Pro, the 25, it's related to the volume of the build box, which is actually in that case 25 liters. And let's say this is really for mid-size production of parts. If you want to go one step bigger, we do have another machine in place, which we call 160 Pro. As I said, 160 liter is reflected by the name. So that's the build envelope, the build volume. That's really mass production, high volume production in binder jetting technology. I still want to mention the machine which is called M-Flex. That is a kind of more for people want to build maybe filters where you have more porous, not a high dense material at the end, a more porous material, then you can scope with that challenge using the M-Flex as well. Core technology. So basically we went through that already, but we said, okay, we have a digital file, we put the file into the machine and prep it, and then this is going to be the recoating step. The inkjet applies the binder. Next step, layer is printed, and then the process starts again. And here, the difference to the powder bed fusion, technology based on laser or e-beam. Here we come to the difference, which is that we have to depowder our part. If it's the sand printers, we have to depowder and then cure the part. If we go for the metal printing and ceramics, that's the same. First, we have to cure, and then we have to depowder. And after the depowdering step, we have to debind and sinter. And that step brings the heat treatment, the furnace people, the furnace technology into place, because sintering as such is a technology which is a kind of an art for itself. So the core business of binder jetting of ExOne is the binder jetting technology, how to print a part, how to handle that process. And then the next step, the sinter process, the sinter step. As the MIM industry is doing sintering since ages, there's a lot of knowledge out there, but it's well known that sintering is not as easy as it should be. And there's a lot of, let's say, experience necessary to sinter a part proper. As we have heard, because there's shrinkage in place, there's different, let's say, reaction of the part given by gravity and other things. We will talk about that a little later. So workflow and process control, we have the 5 steps. We will walk through that 5 steps now. We start with digital print, then we go for materials. I will tell you a little bit more about materials. And the 3D printing process, the depowdering process. And last but not least, really not least, because sintering is so difficult sometimes to predict how the part is going to react, how that works. It's an art for itself. And here, most of the time, you need a consultation and some backup and support from the furnace community, because it's really depending on which material you want to sinter. Is it a 316, so a stainless steel, or you are more interested in nickel alloys, or maybe in ceramics? So there's a lot of room for discussion at the end. It depends really what material you want to produce. But let's go back to the first step, which is the digital preparation. Everybody knows that AM starts with a digital file, an STL file, and to create such a file, that's probably not the problem nowadays. We have a lot of computer power available. We can do that. More difficult to me is to utilize that new power, which is in the old days, in the classical kind of approach, we did the CAD, and then we say, okay, well, we need to go back and redesign. But actually for AM, we could use the method going for computer-aided engineering. And so we have to simulate already ahead how the part may look like to accomplish all the tasks. And that might end up in a part which looks kind of weird. I have seen a part designed by Siemens, which at the end, I thought that's a damaged part. No, it wasn't. It was designed like that, and at the end, the purpose and the function was perfectly applied into that part. We as let's say the traditional way of thinking are just not used to how that part might look like at the end. But it was accomplishing all the tasks 100% and just looked weird. But this is the way, if we understand how we can utilize the power of additive manufacturing to make a part better in function, that is offering a lot of new opportunities. The other thing is that software is a thing, and as you can see here in that screen, coming from digital alloys as well, that there's so many softwares and so many approaches that brings, let's say, all this additive community together, and it's to pick and choose what is the best one. Where am I gonna start? This is sometimes not easy because it's so complex. There is not a one size fits all available, but you have to go through that, and there's lots of companies out there to help you go through. because starting from scratch, it's not as easy. Let's talk a bit about the materials. The beauty of binder jetting is that you can use almost every material as long as you find somebody who produces a proper powder. In the early days, we started with large particle powders. Nowadays, we are able to go for, as I said already, for MIM powders, so very fine powders. And why is it important and why we go for finer powder, smaller particle sizes? Because the sinter process afterwards, if we talk about metals, there is a bit easier if it's finer powder, but then on the other hand, it's not as easy to recoat them. So here we are back again to the technology we have embedded in our machines, which we call ACT, because we want to go as fine as possible in terms of powder particle size, but still we have to scope with the hurdle of being recoatable. Is the powder, can it be recoated in a proper manner? So that means the powder is an important part of our process. And I'm really glad that Mark pointed out that powder is not as powder. You see here some pictures as well. There's very spherical powder. There's a more edgy powder. And all this shape of the powder shape will influence how the droplet is going to be penetrating the layer you have put on top of each other. So this is important that you understand what raw material. This is not just, is it a stainless steel or nickel based? It is as well how the powder size, how the powder particles look like. So therefore, we as ExOne have defined a way how to define or test the compatibility with our process with some little methods, like how is the particle size distribution look like, or how does the flowability look like of the powder. And if you are looking into the definition or the, let's say, specification of powders, you will easily recognize there is a lot of things which are maybe over sophisticated, but on the other hand, you need to really understand what raw material you put into the machines. And that's not just with binder jetting. That is the same thing if you go for powder bed fusion with laser or with electronic beam. So ExOne went through this valley of different powder particle sizes, and now today we are able to use multiple MIM powders, which gives us a very broad material portfolio we can choose by. We have defined some levels of powder or material qualification. So if we as ExOne qualify a powder, then we a third party, then we call it a third party qualified. That means independent laboratory has tested all the steps and the properties of that very powder, went through our process. And if we can meet the typical specifications or standards, as we have spoken about standards, we reach the MPIF standard 35 with the powders or the materials we have qualified as third party. Of course, there's other powders. We have customer qualified materials, which means customer of ExOne has tested and then produced powders, materials, and coming to a proper result. So the customer has proven by his process, by his choice of material, that it works. And of course, there's R&D qualified powders and materials. So there are so many of them, which is then of kind of explaining why not each and every material which is existing can be a fully third-party qualified powder. Because if you're gonna do that, then it's a report by an independent company telling us this is tested by tensile, by hardness, by impact, and all the other things that is really committing and tested against the MPIF standard, and if we are successful by doing so. Third party qualified, for instance, ISO 17-4, 316L, the M2 tool steel, and very new is the Inconel 718. If we have a quick look to customer qualified materials, Then there's by far more to come. There's the ceramics and beyond even metal ceramic composites, silicon carbides infiltrated with silicon. So this is sometimes the beauty of binder jetting. And on the other hand, it's a burden, because to pick and choose the right material for the right process, for the right application, is sometimes offering so many opportunities and so many choices that it's not easy to make your own judgment what is the best. Here you see just a small a number of parts of metals. That's not everything what we have tested. We have tested hundreds of them, but it depends on what the customer needs. Sometimes it's his own developed alloy, or it's a very standard alloy, like maybe a cobalt chrome or an H13. You will reach, as I said, the typical properties of the metals, as assuming they have produced by a MIM powder or a MIM process. This comes for, or goes for all the others as well, for the M2 steel. Well, one thing is, if you talk about materials, one thing is the powder, the metal, or ceramic, and on the other hand, it is about the binder. It does has to fit together. So it's not easy. It sounds sometimes very easy, but you need to find the right binder for the right material to achieve the best properties you want to achieve. This is why we as ExOne, we do have 4 binders. Every binder has its pro and its cons, depending to what is your target application, what is the alloy you want to print, you want to sinter, and what is the application behind. So we have 4 of them, because we have understood that there is no one size fits all. One binder which is giving all the properties you want, and probably there's by far more possibilities to develop some other binders. But at a certain point of time, you have to decide whether you want to stick with a solvent binder or a water-based binder. Some even may choose the phenol binder because they want to go for a tungsten carbide. Well, the printing as such, the video has explained it properly how that works. But it sounds very simple, but sometimes it's not as simple if you go through the process. Yes, there's the drop formation, so how the firing of the printhead works, and how big and how the size the droplet has, and then how it hits the surface of the powder and then starts to penetrate. Because you want to make it penetrate only as deep as you want it. So in the C direction, we don't want to that it's gonna bleed out. The same comes to that we want to form a voxel and not a bleeding out and left and right. And this is the difficulty to do the binder jetting in the right way. What we have decided by using a technology, the piezo technology, rather than the thermal technology, to spitting, to firing the droplets into the powder bed, because we think we get a bit more a precise way of printing or creating our droplets. Curing. And now that's going to be curing and sintering. You can do binder jetting, but without the depowdering, the curing, and the sintering step, binder jetting, the green part means nothing. So you need to post-process. You need to debind and to depowder and then sinter a green part which we have printed. It's important to understand that this belongs together. One thing is printing, the other thing is then the depowdering and the sinter step. So curing your part is necessary to, let's say, cure the binder, so curing the glue between the particles to make a solid part which you can handle. It's still not solid as you think, because it's in that green state. That means it has a tensile strength of something like 6 to 8 megapascals, so it's kind of fragile. And as we don't want to have a fragile part, after the depowdering process, we go for the sinter process. And why is depowdering so important? Of course, because if we're gonna into the sinter process, each and every particle which is in the part, if there's remaining powder, it will be sintered to a solid block. So we don't want that. So we have to depowder in a proper manner. Sintering. Of course, the furnace consideration is very important. I just give you an example. If you choose to go for stainless and you think in the early stages you want to start printing and sintering a 316, so a stainless steel, and the next day you will think about maybe we go for a 17-4. I think that's even sounds similar and sounds even very familiar, but if you want to achieve the best possible property of a 316, you should go with hydrogen or high vacuum into the sinter process. And there's so many ways and so many combinations of material and the way you're going to sinter that you need an expert telling you, like the furnace companies, like Seco Warwick, how to do that. It's not us as machine build. As we build the printers, we can do the binder jetting process, but the sintering, of course, for the qualified materials, we know how that works. But if you choose and pick another material, that's a different animal, and we need to find out how to sinter that in the best proper way. If you have gone through all the process steps, there is the shrinkage we mentioned. So there is a shrinkage happening while we print, and then we're going to sinter, and that has to be understood because the part is not ready as we have printed it. We go through the sinter process, and yes, there is shrinkage. So you see on that picture the black bar and the gray bar. So this is something like how much of a shrinkage you're going to achieve or you're going to face in that process. And that makes you really think about, okay, what is important? I need to redesign in a proper way. I need to consider the shrinkage. Everything which comes along with shrinkage is as well belonging to how you start. That means how the green part, the green density looks like. And this brings me to the point why we have decided going for MIM powders, because there we can reach a higher green density that brings us less shrinkage and, even more important, tighter tolerances and less distortion. On the other hand, of course, you need to already consider that before you're going to print, how that distortion might look like while you go through the sinter process. And an advantage on one hand is, of course, for the binder jetting technology that we don't apply heat like the powder bed fusion with laser, which is welding, little layer by layer welding creates a different grain size or a different grain structure while doing so. And with binder jetting, there's a different, and the sinter process afterwards, there's a different approach without the temperature and the potential segregation which might happen in the grain size build. Well, there needs to be design guidelines, of course, because yes, it's not one in, one out. That means we have these scale-up factors we need to consider for the printing, shrinkage. And now, as we spoke about, you may understand why it has to be the right part dimension, the right design for binder jetting. Not every design fits to being binder jetted. And this is where we as ExOne try to have a close communication with our customers if that fits to their needs. Because, and Mark has mentioned that as well, not each additive manufacturing process does cover the needs of the customers. If you have done that by milling and drilling, maybe you should stick with that because it's just cheaper. But if you go for casting, maybe you're still gonna cast it. But if you want to add some functions or you want to change, tweak some designs, then this technology is the one you go with. ExOne, we do have a printing service. That means a job shop based in US. So in Americas, people can order printed parts from ExOne, not just buying a machine to print themselves. We as well offer a material 3D printing solution shop. And this is for me one of the most important slides, because I think, yes, binder jetting or additive is a nice, very sexy technology, but you need to be aware of as well the strength, the weaknesses, the opportunities, and the threats which comes along. And there are some. It's not just the golden glory technology. You need to think through, does that mean an advantage to me at the end? Is that bringing an advantage? Is maybe the part adding value to the supply chain I'm looking for? And there are some risks linked to that. We need to face and we need to discuss with the customers. And not every additive manufacturing process is easy to adapt. We know that. And we will give a helping hand to our customers, explaining if that is maybe a good opportunity, or maybe they need to rethink if they want to redesign the part to be binder jettable. So as well, a threat to me, or not a threat, it is important to understand that binder jetting and sintering belongs together. So the heat treatment is one important part of binder jetting. And this is why here today with Seco Warwick, we're gonna explain the binder jetting a bit more in detail, because sintering, and that means we need furnaces to do so, is so important, and do that in a proper way. But if you have found a way to print a part, considering all the distortions, the shrinkage, and prevent some distortions, then you can fix that process and produce parts, a lot of parts, in the very same way if you have a proper setup of machine and of the furnace. So, summary, just in brief, great opportunities, but please consider it case by case, application by application, and the design and the part has really to fit to all of that process steps. Not just, oh, it's easy to bind a jet, but how to depowder or how to sinter. Go through the process, think about it, maybe you want to redesign, and then it's easier to do so. But there's so many opportunities out there by binder jetting. And we are more than happy to help, to give you a helping hand, to give you support, and have a discussion about your needs and about the needs of the additive manufacturing community. So, part, function, material, geometry, and requirement, that ends up in a great opportunity if you find the right way through. Thank you, Richard. I hope that was in time for you.
Well, Oliver, thank you very much for a knowledgeable presentation. Me personally, I'm a huge fan of binder jetting due to the fact that, as you mentioned it always required a heat treatment, and this is the place where Seco Warwick can step in. So this is definitely a huge opportunity for Seco Warwick and entire heat treatment community to make some contribution in the technology development. So speaking about heat treatment and sintering, you mentioned that there are certain challenges that binder jetting is facing, like the shrinkage idea. Do you think that somehow heat treatment can help to overcome those challenges for binder jetting in general?
I think we don't have to overcome it, actually, because the MIM industry is used to shrinkage since ages. So it's not a very unknown animal. It's just the way you approach it. If you take it as it's given and you understand how to handle it, that's a challenge you can scope with. A bit more challenge is that we are still waiting for software. We are waiting for software for prediction, how that shrinkage will work, how that will affect your part. But the good news is that there has already been people like Ansys, like Inspire, like Altair, starting to looking deeper into the prediction, the algorithms which are necessary to predict a sinter process. So I think we are on the right way. Additive is a new technology, and there's so much room for improvement, even as well for the heat treatment. Because if we know how to predict the shrinkage, then that will ease the life. And I think in being supported by the furnace community, there's a great opportunity out there.
Okay, I really like that idea that this is the part of nature of the process and we shouldn't fight with it. We should try to live with that in a harmony. So that's quite nice. As for the challenges for 3D printing, metal 3D printing and binder jetting, do you think that in the nearest future it will go in the direction where the companies will be fighting for the biggest size of the printed parts, or maybe the speed of the printing, or maybe the material development, or maybe the quality of the printing, like resolutions and so on? What do you think? What will be the biggest challenges for upcoming future?
Richard, you asked the question which is asked by the entire industry. And the trick is that the industry is kind of impatient. The CNC machining, it took 40 years to come to a stage where we are today. So additive has not the time at the moment. So we need to accelerate. Everybody understands we need to be cheaper, faster, more precise, more sustainable, and more, let's say, constant in results. The good news is it will work. We are on the right path, but maybe we need some time, a little more patience by the industry that it's not as fast as they want us to be. We will reach that point for sure. And we have a great opportunity and community out there in the AM world. So if the people work together, we can achieve that.
Okay, so patience is the key word for that.
It is.
Okay, so the last question. I also wanted to ask you about the ecological aspect that I asked Mark. What do you think in terms of binder jetting? Can we consider it as a super ecological technology for upcoming generations?
I would agree with Mark. He brought up the example of a 100-pound block, and if you mill and drill it, that at the end you have a maybe 5.5 pound part. And this is really offering a lot of sustainable potential, that we can reuse the powder. We don't have to scrap it. We don't have to put more energy into the reworking process. So this is what comes into play as well, the sustainable aspect and the efficiency of the process, and which is underestimated and judged at the moment as well, is all the parts don't have to be on stock. The operating working capital is immense, which people have in their warehouses. We can reduce that, and maybe that's the one and only good thing of COVID-19, that the people have understood that the supply chain, we need to rethink one or the other time, and not waiting or having all of the material on stock, or think that we can get it from China or from somewhere on some other point of the world as fast as we have done that in the past.
Definitely, I can agree with you about that. During the COVID situation, we heard a lot about the situation when the current production profile was simply not efficient, right? And all of a sudden, some students came with help, right? They start printing elements necessary for hospitals and so on. So it was really, I believe, it opens a new era, and it shows that additive manufacturing is first of all, the most flexible and adjustable technology available on the market today. And I believe that's the sound of the future. That's the sound of the future, definitely. Oliver, thank you very much for your presentation. Thank you very much for your knowledge. Mark, are you still with us?
Yeah, I'm still here.
Great, thank you very much, gentlemen. I would like to thank you once again for your participation. I think we nearly touched the essence of additive manufacturing, but unfortunately time is a limit. I believe we will have chance to continue that story in upcoming seasons. So definitely please stay tuned with us. Thank you very much. Bye-bye.